This conference will now be recorded.
Yeah, Varun. Yeah. Yeah, we can start then.
Okay.
Yeah. So, should I start with bias then first?
I thought of taking them through drift.
Yeah. Okay. Yeah, first you can take them. Yeah.
Yeah. Can you all see my screen?
Yes,
Yeah.
Varun.
Okay. Do you know anything about drift? I mean, what exactly do you understand when you hear the term drift?
No, this is the first time I've been listening.
Drift means like change from the reference point or something like that.
Yeah, exactly. That's correct. Yeah. So, what happens here is, generally when you train a machine learning model, you train it on, a particular data set, a training data set, and each feature will have its own distribution of sorts, right? Now, if your model generalizes well, it is able to tolerate certain deviations in that distribution. So, maybe, the mean is off by a little, or, the curve, a curve which is looking like a normal distribution has, flattened and, got widened a little bit. All those changes can be handled by a model if it has generalized well. But, even a good model can only tolerate so much. So beyond a certain point, you need to figure out whether, whether it will impact your model or not. And in order to do that, you need to monitor your data distribution in the first place. So if you are getting, distributions for each feature which are drastically different from what your model got trained on, then maybe that model is not the correct one. So it is time to retrain your model. So, data drift is one thing that will help you decide whether you would need to retrain your model or not. Am I clear till here?
Yeah, Varun.
Okay. Okay. So, yeah, I'll show you this thing. So these are the features which went into this particular random forest model. Okay. And you have loan amount, mortgage due, property value, and many other such features. And you can see, the thing in yellow is the production data set and the thing in blue is the validation data set. So think of this validation data set as your reference data set or your train data set. It's something against which you compare other distributions to, right? So this is your validation data set and this is your production data set. Now you can clearly see that both these distributions are following are pretty much similar. It will be more clear if you see mortgage due. So the distributions are pretty much looking alike, right? So for mortgage due and property value, years on job, reason, or number of derogatory reports, the production dataset and the validation dataset, they are following a pretty similar value. Pretty similar distribution. Now, if you look at CL age, you can see that there is a deviation. Not exactly a deviation. You can see that, the curves are looking different for the validation dataset and the production dataset. So, you might wonder, is this, did the dataset drift? So, looking at it, you feel that, it might have drifted, but you're not really sure. You're not entirely sure that, whether the dataset has drifted or not. So, in order to determine for sure, and in order to, reach a conclusive, conclusive answer, whether your dataset has drifted or not, you need to perform a statistical test. You must have studied about, t-test, f-test, and various other tests in BA with R, and all the other subjects, econometrics, all those things, right? So we need to perform a statistical test against the two distributions in order to determine whether they have drifted or not. Now for continuous features, continuous features like CL age or delinquency or years on job, we perform a KS test. So KS test is called Kolmogorov-Smirnov test. You can just look it up to see how it works, but that is what we are using for numerical distributions or continuous features. And then for categorical features, we are comparing the two distributions using chi-square test. Now now we can see here that each of the features says there is no drift, and the p-value is quite large. So anything less than 0.05, we would say that the data set, not the data set, the features have drifted. So the validation data set and the production data set are following two different distributions, and it is just an indication that your model might not perform as well. The model's accuracy might go down, or any other metric you're using to calculate your model's performance, the model's performance might go down. So this is just indicative of that. Whether it has really impacted or not, we would only know after we run the model and then score on the production data set. And then you can compare the confusion matrix and all the other features against the previous data set to know whether your model's performance has gone down or not. But this just gives us an indication as to whether your model is going bad or not. So over here in this particular in this particular scenario, there is no feature which has drifted. Everything is fine, and your model metrics are pretty good. Your accuracy is at 96%, and you know uh, it's looking pretty good overall. But if you look at another data set, now in this data set, what we did was we actually introduced some noise into a couple of features, and then we ensured that the data drifted. So if you look at years on job, visually you might see that you might be a little bit confused. Okay, this looks like it has this looks like it has changed, but is it changed sufficiently enough to cause drift? So that we can identify and conclude by performing the KS test, as I had mentioned before. So the p-value is 0.0. I mean, it is a very small number. It's not exactly 0. It's a very small number, but it is less than 0.05. Therefore you reject your null hypothesis. Now null hypothesis in this case is both the distributions are identical or similar, and your alternative hypothesis is that both the distributions are not identical. So your testing has conclusively proved that you need to reject your null hypothesis. These two are not the same distribution. So that is how we figure out whether your feature has drifted or not. Now for years on job, that is one. And then you can clearly see for debt to income ratio that these two distributions are completely different. So one is flat and wide, and one is one peaks at what uh, somewhere between 35 or 40, right? So these two distributions are completely different. So your model got trained on a distribution which looks like this, the one in blue, and what you're getting when you deployed the model is the one in orange. So your model might not do a very good job in predicting, and if you see, your accuracy has gone down, your F1 score has gone down, your metrics will definitely go down. And you can also look at other statistics, like this is a table of all your features and the test statistics. So for continuous features, the test statistic is your KS test, and for categorical features like reason, you have chi-squared test. And one interesting thing here is the distance. So the distance is the distance between the two distributions. Now we just included this just to give a measure of how much the distributions have deviated from each other, but we necessarily do not take any decision on this. It is just a good to have feature, just to know how much each feature has drifted from each other. Now if you see, features like loan amount, mortgage due, and property value, none of them have drifted, and the distance between those two distributions are quite small. But if you see years on job, the distance is considerably larger than the others, and you can also see that they have drifted at all levels of significance, at 10%, 5%, and 1%. Any questions still here?
Varun, the p-value seems to be high, right, for the features that are not drifted.
Yeah, that is correct. You're
So
not
are
rejecting
they,
the null. You're not rejecting the null, right?
so
Yeah.
in general case, are they statistically insignificant to the target variable?
No, that is no. You should not link it that way. So this is not like your linear regression where you look at all the p-values for your coefficients and then say whether that feature is significant or not. No, this is not how we are looking at things. So this p-value will only tell. So the test is completely different. Over there, you are performing an f-test of sorts. As far as I remember, you're performing an f-test. But here, what you're performing is a KS test. Now, this KS test will only tell you whether distribution A and distribution B are coming from the same population or not. That's it.
Okay.
Whether they're identical to each other or not. So, just because you're getting a high p-value here does not make it insignificant, or just because you're getting a low value does not make this feature significant. It only tells you whether you're able to reject the null hypothesis or not. That's it. And your null hypothesis is that both the distributions are identical or they're coming from the same population. That's it.
Okay, got it.
Yeah. And we also have this summary screen. So these are your, so the first time we ran this thing, so the way this thing works is you have data sets which are coming in at different points of time. So you could have data which is coming in weekly, or you could have data which is coming in monthly or once in 3 months, whatever the frequency. We just need to run it against your reference distribution and then determine whether your features have drifted or not. And over here we see the first time we ran, you can see these scores. So when I opened this and I showed you these numbers, these are the same numbers which show up in your summary. Okay, in the summary you see that your model is performing pretty well. You can see all the numbers are between 80 to 100, and as time goes by you get another data set. However, features have drifted here, and you can see that the model performance is going down. And this is how you know that your model's performance has gone down, by looking at this thing. And then to determine which features have affected your model, you can just go and look at the graphs, or you can look at the table to see which features have actually deviated from what they are supposed to be, and then are causing problems with your model. Any questions? I mean, this should be pretty intuitive.
Yeah, when it's clear, you can move it. Like,
Okay, all right. Aditi, I think you can take them through bias.
Yeah.
I have one doubt, although Varun,
Yeah.
regarding the drift, right? So,
Mm-hmm.
uh, correct me if I'm wrong. The bias detection is telling whether bias is all about how the production data set is matching the validation data set, right? So it is like negative bias,
Drift.
No,
positive.
that is the data drift thing,
Yeah,
not
that
bias.
is data drift.
Okay.
Uh, you meant right. You said bias, right? Bias is when you compare the data sets.
Yeah, yeah, yeah.
No, bias is not that. So that is data drift, which Varun just explained.
Okay, okay.
Okay, so I can take you go through bias detection and mitigation. Yeah. Okay, first I can give you a brief introduction about what is bias. So bias is basically a phenomena of observing results which are systematically being prejudiced due to some faulty assumptions. Now there can be, these faulty assumptions can be made during any algorithm development process, or there can be faulty assumptions during in the training data itself, right? So this tool, XAI tool, where of bias detection, is basically detecting and mitigating bias in our machine learning models. So and how it does is that it detects and measures these discriminatory behaviors in a protected attribute. Now, what are protected attributes? Protected attributes are those characteristics or qualities that by law cannot be discriminated against. Now, for example, we have gender. So we see bias, right? We see generally there are discriminatory behaviors between men and women. We have age, then we have marital status, then religion, then any socioeconomic status. So those are protected attributes, and this tool helps in detecting and mitigating bias by finding any discriminatory behaviors in those protected attributes. Now, I can take you over through the tool. Okay, first of all, in order to create the bias, although I've already created one instance, but I'll tell you how we create that. So in order to see or in order to analyze bias, what we need is a production data set. Production data set is any test data set on which you want to detect bias or mitigate bias. So let's see, I can select this, right? And once I select, you can see these three things got populated. Now, this test data set or production data set is in the format of, it also contains two additional columns. One is the column with target Y true labels that are ground truth labels. And second column is our Y pred values, predicted values basically. So it contains two additional columns. Now it's asking us to select the ground truth label. So in our case, we have loan status. Okay, so let me first explain about this data set also. So it's a loan application data set where we have general information about our applicants, like you have gender, credit history, marital status, these informations. Now, and what are we predicting? We are predicting their loan status, whether it has been approved or denied. So I'll select the ground truth label, which is our loan status, the predicted column label, which is our loan new status. Now here it's asking us to select the protected attribute name. These are the columns or features on which we want to assess or analyze our bias. So for simplicity's, I mean, let's say for simplicity's sake, I just select 2 or 3. Yeah, and let's go to the next page. Now this page is just describing about the features, nothing else. What is the minimum value, maximum value, type of the feature. And after we submit, it will create this analysis of the bias. Yeah. So this is the page. Now, first of all, we are showing the overall model performance metrics, which are accuracy, precision, recall, selection rate. And then, so in this case, I selected the feature gender. So it is showing me the analysis of bias for this feature. Now this feature has two subgroups, female and male, and we will analyze those subgroups as well. Now this tool helps in identifying and estimating the bias in the machine learning models, as I said previously, using various fairness metrics. Now there are different fairness metrics, but we have used just 3 different fairness metrics in order to show. So one of them is the demographic parity difference, equalized odds difference, and demographic parity ratio. Now, demographic parity, or you might have heard about disparate impact or demographic parity, right? So I can tell you what exactly this is. Now, disparate impact is, so first of all, these fairness metrics, why we use these fairness metrics. So these are basically these are helping us to verify whether our machine learning models have, they have not produced any unfair outcomes across these subgroups, male and female. So demographic parity is, it's basically the proportion of favorable outcomes between both the subgroups. So I can give you an example for that. So if I say demographic parity between male and female, so there I'm taking the proportion of favorable outcome in male and in female. They should be equal. So the proportion of loans getting approved for male should be equal to the proportion of loans being approved for females. Any questions?
No, Aditya.
No, Aditi.
Then I can go ahead. Similarly, so this is what demographic parity is. And the difference is, so demographic parity difference is when we take the difference of the favorable outcomes between male and female. So that is the difference. Similarly, demographic parity ratio, here instead of taking the difference, we are taking the ratio. So ideally, if we are taking a difference, the ideal value is 0, right? If we are saying that the demographic parity difference is 0, that means we are saying that the favorable outcome of male is equal to the favorable outcome of female, right? Ideal value of this metric is between 0 to 0.1. Similarly, for equalized odds difference, we have 0 to 0.1. And for demographic parity ratio, we have between 0.8 to 1.25. So here we can see that this is going above this threshold. So yeah, our machine learning model is producing biased outcomes. Similarly, for this, it is also exceeding the threshold. And similarly for this. And we can further analyze this by seeing this. So there are different model performance metrics we have listed down for each subgroup for both female and males. So now here we are seeing the accuracy, precision, and recall for both of them, and as well as the error rate. Now, error rate is basically showing us the distribution of errors amongst these subgroups. Now, the yellow part you can see, these are the under prediction values, and the blue ones are the over prediction values. Under prediction values are saying that our model, our model predicted more unfavorable outcomes when it should have predicted when the actual values were favorable. So for example, there are around 35% of the females that were not granted loan, but the actual value was, when in the training data, the actual values were that these females were granted loan, and our model predicted them. They were false positives, right? False negatives. And similarly, around 6% of females were granted loan when they shouldn't be granted. And same for males, we can see the over prediction and under prediction values. But here we can clearly see that our model is predicting biased outcomes for males, right? From here we can see this. Now, in order to analyze more, we can see that the selection rate. Selection rate is the rate of positive outcomes that our model predicted. So our model predicted around 67% of the males were granted loans, and around 29% of the females were granted loans. So this is clearly showing that more males were granted than females. Yeah. Any questions?
No, Aditi.
Yeah. So now that we have analyzed or detected the bias in this feature gender, we can perform mitigation on the same. Yeah. So similarly on this feature gender, now that we have an detected bias, we can perform mitigation as well. So we can see the fairness metrics here. So now in order to mitigate, we are using two different algorithms here. One is disparate impact remover and another one is reweighing. Now these two algorithms helps in mitigating bias. There are different techniques that they use in order to mitigate the bias. Yeah, so here you can see that the orange one is the disparate impact remover, which is still this fairness metric is showing that it has exceeded this value, this threshold value. But when we are performing this algorithm, reweighing algorithm, it is beyond this, it is in between this value 0 to 0.1. And here we can see in equalized odds difference, both of these algorithms are, they are exceeding this threshold. But here in demographic parity ratio, this algorithm is working fine because it is in between. Yeah. And here we are comparing for both, and in fact for all of them, pre-mitigation and after mitigation, what is the result. So we are comparing the accuracy, precision, recall of the three. And here we are comparing the error rates of all the three. So here you can see that around where before mitigation during the detection part, we can see that around 35% were, the under prediction value was 35%, but it reduced to around 5% after performing the mitigation techniques. And when you are seeing the selection rates, you can see that when we detected the bias, it was around, it was this much. And when we are applying these algorithms, it got reduced and around like 64, the disparities are very less now. The differences between these two selection rates are very less now. So this is about bias detection and mitigation. Any questions? Guys, are you there?
Yeah, Aditi.
Yeah, so this is about our tool where like we are explaining, we are showing the data drift, and we are also detecting and mitigating bias. Now, what you guys can do is that you guys can research on how we can enhance this tool. I mean, you can get your ideas how and what we can do in all these three areas.
So do we get the access to work on the website, Aditi?
I can give you this the link and the username and password so that you guys can see this.
Okay.
Yeah, I can give you that. And in the weekend I can work on the documentation part. So we'll send you one.
Sure, that would be helpful,
Okay.
Aditi.
Yeah.
So, just one question, Varun and Aditi. Like, if we have to start doing the enhancement or anything, so how the backend looks like, how do how the back this is the entire front end thing, right? So the backend, how to work on that one. So just want to understand, like, how do you deploy your code over here?
I mean, you don't need to worry about all those things because there's a platform engineer who will be, taking care of all those things. So deployment, scaling,
Oh,
and all those things. Productionizing your code is not your responsibility. You just need to, ensure that your methods or functions or whatever you define are working
uh-huh.
properly. That's it.
Okay. And for testing also, how do you do this in test environment, not in prod environment? Like in your local, you test it?
Yeah.
Okay.
Yes.
Okay.
Hmm. Yeah. So like what you can do is you can look into different libraries that we have used here, like in explanation and global and local. In bias, I mean, we can list down the libraries and you can look into that. And additionally, whatever research you do, you can.
Okay, Aditi. Yep. Sounds good.
Yeah. Any other questions? No.
Uh, we will look forward to that document and